What is the difference between a complete and total understanding of the brain's neural process for eliciting the colour red and the experience of the colour red? Or what about our experience of something like morality, music, love, or, as only the Germans could put it, the feeling of Abgrundansehen, the overwhelming need to look into the abyss? Can an understanding of neural activity give us all that we need to explain what experience is? And if not, how much more can the hows of this physicalist philosophy teach us? Thus far we have identified the biological surface where the flimsy, influenceable and ever-changing self gets presented to us, where the brain lies the mind into existence. But much of our discussion has been concerned with this issue of change, of a self experienced in time. So let us return to our earlier topic of time and see if a deeper knowledge of its hows can't offer some insight into this ever-shifting theory of self. In recent decades, there has been a growing case for the theory of quantized gravity, the idea that space and time are digitized. But how could this be possible? And what does it really mean? And even more curiously, what would be the nature of reality beyond the quanta? In 1950, physicist John Wheeler proposed that at the scale of Planck's constants, Planck length and Planck time, we hit upon the smallest possible lengths in the resolution of spacetime, below which Wheeler theorized a flux of quantum foam, a place where concepts such as left, right, up, down, near, far, and even now and then become so scrambled as to have no meaning. An idea that is so counterintuitive that we hardly have a language capable of describing it. Practically every word is in some way bound to either a spatial or temporal framework. And yet, in this strange and alien landscape, even the claim of being below this scale becomes nonsensical. But what is it about Planck's constant and its underlying equation that suggests a description of reality as radical as that offered by Wheeler? In the late 1800s, physics had hit a roadblock. A conflict between mathematical and experimental evidence that unveiled a definite flaw in the way we thought about atoms and the way they radiate energy. The understanding at the time was that black bodies, which is any body that emits electromagnetic radiation, be it a light bulb, a star, or even a human, should be capable of emitting this radiation via any frequency found along a continuous spectrum. And as these frequencies become further compressed and move towards higher and higher energy states, one should also find a corresponding linear increase in the emitted radiation. Essentially, what this would mean is that the more we push into higher frequencies of light, transitioning from reds to blues, the closer that radiation levels should reach towards infinite energy. But considering that blue light fails to showcase the qualities of a death ray, we know for a fact that this is not what happens. Instead, at a particular threshold, the radiation level unexpectedly bottoms out. Dramatically dubbed the ultraviolet catastrophe, it was Max Planck who, in what some have referred to as a frustrated last-ditch effort, altered the equations, theorizing that it was impossible for atoms to emit radiation at fractional dissections of particular intensities. And almost accidentally, it solved all the problems. All observational data matched Planck's calculations, and thus the quantum theory of energy was born. Energy, it turned out, was quantized. This theory, confirmed in a related experiment by Albert Einstein only a few short years later, showed us that even light was made up of these minuscule packets of energy. Photon-sized bundles of energy that pass from one electron to the next. A world of parts, giving rise to not only light, colour and heat, but also the repelling force we feel when pushing up against a solid object. Everything, every force, was made of fundamental quanta. Everything, that is, except for gravity. It wasn't until the theory of relativity came along in 1905 that the true implications of Planck's discovery could be made clear. By combining the three now known fundamentals of Newton's gravitational constant, Planck's own quantizing constant, and Einstein's limitations on the speed of light in a vacuum, Max Planck could now describe a measurable quantum limit. The Planck length was 1.616255518 by 10 to the power of minus 35 metres, a fundamental unit that could describe the minimum length, duration or mass of energy. And the smooth, non-quantized description of gravity found its place as the warping of space-time. Gravity was space-time, the backdrop to the quanta. There was only one problem. It still didn't work. Actually, it worked extremely well, except for the fact that our understanding of gravity with respect to the very large and gravity with respect to the very small didn't form a unified theory. Instead, we now had two very distinct ways of describing our universe, relativistically and quantum mechanically. Each accurate and, according to all observational data, correct. It's just that they didn't work together. A unification of classical and quantum physics is still today considered the holy grail of physics. But it has been this hint that gravity is the only force in our universe not to be quantized that has since led many to assume that any theory of everything should likely include a quantizing of space-time as well. The universe, they say, could be conjured by pure mathematics. And it is this that led Dr. John Wheeler to hypothesize his idea of quantum foam, the domain beyond, where space-time fails to operate as a continuous analog agent. Planck's constant, denoted by the letter H, can be found at the heart of any quantum mechanical theory, especially those attempting to bridge the gap between relativity and quantum mechanics. Theories such as quantum loop gravity or string theory go so far as to include Planck's constant alongside Wheeler's theory of quantized gravity, suggesting that time, at a fundamental level, might not exist as a continuous agent, but instead emerge as a property of the fluctuating quantum units of space. In superstring theory, this quantizing of space-time can, in extremely basic terms, be visualized simply by imagining a shrinking circle. If the nature of this circle were quantized, then there would have to be a minimum value that it could shrink before turning in on itself and beginning to grow. These theories also talk to the mysteries at the start of the universe and suggest that rather than the universe beginning with a bang, it may have begun with a bounce. As one universe ended, passing through the eye of the space-time needle, it turned in on itself before expanding outwardly in all its current directions. Such a granular nature of space-time would also eliminate universal infinities and singularities, previously argued as an inevitable occurrence of nature. Quantum loop gravity, similarly, describes reality at the Planck scale as a net of finite loops. To represent space-time in their calculations, physicists use a 3D grid called a lattice of quantum chromodynamics, or LQCD. Upon this, they calculate the actions of the quarks that make up the protons and neutrons of an atom. Upon the lattice, force-carrying gluons move about in a beautifully complex dance, with each element influencing the next, building towards a chaotic complexity that can only be untangled with our most powerful of supercomputers. When first attempting to rectify the enormity of this mathematical puzzle, Schrödinger, in his correspondence to Einstein, referred to it as a gift from the devil's grandmother. Using the LQCD, physicists placed the quarks in their respective positions alongside the force-carrying gluons that hold the quarks together. Then, step by step, they closed the gaps between the quarks, taking into consideration all the many complex variables. At Planck scales, due to a charge of energy inherent in the gluons, they found that gluons would spin upon themselves in a loop outside of their relationship with the quarks. These were loops of force, loops of gravity. And it's these loops that inspire the theory. For these loops don't exist somewhere within space-time. They are space-time. Loops that knot and weave together to form a net called the spin network, thought to be the smallest resolution of space-time, the quanta of volume, area, and duration. However, there is no evidence in either model to support a claim that such a quantizing of space, if found to be true, should be a final or ultimate roadblock in the path of reality. And neither is this what the theory's proponents are attempting to prove. If real, this would merely be the scale where the geometry associated with directions in both space and time become emergent in their known forms, hence the chaotic flux of Wheeler's foam. Like all previous examples of emergence, we are never offered any ultimate one-sided boundary. Just as at the scale of the atom, we pass beyond the scale of matter, and at the scale of the photon, we pass beyond the scale of light. Here, we may pass beyond the scale of space and time itself, into the next perspective of this infinite flux. Time would, therefore, have an emergent nature, not too dissimilar from how a wave upon the ocean emerges from the molecular connectivity of water molecules, or how our fluid consciousness emerges from the quantized firing of neurons. Now, at this polemical point, I want to take a quick moment to return to what has been said in prior chapters about this idea of emergence. As you might think, these two metaphors are merely a playful spin of language. You may even be able to offer reasons why they're entirely unsuited as metaphors for this relationship between fundamental space quanta and emergent time. But what I feel that these and all other examples of emergence share is a quality of perspective, highlighted by the fact that emergent properties are not secondary to their more elementary parts, at least not in any ultimate sense. This was the insight of previous chapters, that this quality of emergence should be more accurately described as a new perspective of what is fundamentally one and the same phenomenon. The act of missing in terms of the greater picture. So, yes, a wave emerges from the molecular connectivity of water molecules, and as such, the wave's behaviour is in many ways determined by the character of its molecules. But so is the collective behaviour of the molecules determined by the nature of the wave and its surrounding environment, i.e. the water. The point is that influence passes both ways. But the reason why we tend to presume a strictly bottom-up hierarchy is because, well, you can't have water or waves without water molecules, whereas you can have water molecules independent of water. And that seems reasonable at first glance. However, there is another way to look at this picture. Because we can't have a wave without both water molecules and water. So what does this say about the assumed hierarchy? When we consider the wave uniquely and its shared bottom-up, top-down framework, we can see how it attains its unique identity. Firstly, we notice that the wave clearly isn't synonymous with either water or water molecules, because it's the wave, hence the name. Plus, as said, the wave has a unique influence over both environments in how its nature dictates their movement. But though the wave, as an ontological structure, is full of its own character, and so in that sense independent, we are also forced to acknowledge that there is nothing other than these two classes of environment, inner and outer, and their relationships in all that we call a wave. The wave doesn't exist on its own. And so it's therefore clear that this particular relationship, named the wave, only attains an identity from within a perspective that explicates it from the unity and activity of the whole. From one perspective, it is itself just the wave, whereas from another, it's just the behaviour of the molecules, or equally, the behaviour of the water. But isn't that also curious? How some attribute, the wave, could be the behaviour of two different classes of things uniquely. How it could be the behaviour of both the water and of the water molecules. The reason for this is not simply because the water and its molecules are in fact the same thing, because ultimately they're not. Once again, water and water molecules are not synonymous with one another, as they each have their own characteristics and identity, both of which hold a particular influence over the other and their shared environments. The reason why they can share the same wave as a characteristic of their independent nature is because neither the water nor the molecules have an identity that is any more ultimate than the wave's identity, as they too are merely the characteristics of some other broader system. Like the wave, for the water to exist, we must presume its inner and outer environment, i.e., the molecules in the planet's atmosphere. From one perspective, water is undeniably just water, and yet from another, water, like the wave, is nothing other than the behaviour of the molecules or the behaviour of the atmospheres, a relationship held between two straddling environments. Water is the crosstalk between the molecular world and the greater atmosphere, in just the same way that the wave was only the crosstalk between molecules and water. Neither exist as entities in and of themselves. Now, this may all sound like superfluous verbiage, but we could have just as easily gone in the opposite direction, towards the inner environment, and appreciated the molecules as nothing other than an overlapping of related environments, this time between the atoms and their broader microscopic world. If we remember, the reason for the assumed bottom-up hierarchy was that we could have a molecule independent of the water. But again, there is nothing other than the behaviour of atoms and their relationships with other local atoms in all that we call molecule. Molecule is just another class of relationship, something that has influence and identity within a certain perspective, but is nonetheless devoid of any unique substance. How it gets explicated from the activity of the whole depends on how strongly a certain perspective focuses on its characteristics over another. And this is an unfolding that happens ad infinitum. In fact, simplifying any unique identity down to the relations of just two environments is itself a gross simplification. It's also a subjective pluralizing. In actuality, any identifiable entity can either be considered the crosstalk of a seemingly infinite number of environments, or just the one. Everything is the emergent characteristic of everything else. Which only goes to show that what might seem digital in one perspective shall be the basis for what appears analog in another. with influence always passing in both directions. In a similar fashion, the digital behaviour of neurons might affect the analog experience, but so will that experience dictate the behaviour of the neurons. Though a neurobiologist may be able to describe the digital neuronal algorithm that corresponds to the feeling of Abgrundanziehung, how we experience it is as a continuous process. We need only to think about our experience of music to see how we conjure a living moment. And yet, it is this experience that dictates which neuronal algorithm shall be the next to follow. Even Wheeler himself recognized this duality of perspective-oriented relationships, stating, quote, "Space-time tells matter how to move. Matter tells space-time how to curve. Two sides of one coin." The point that we've already begun to unpick is that emergence is rarely the unidirectional evolution of states that we tend to envision, with more fundamental structures giving rise to higher orders of complexity. Instead, new relationships attain a particular power of influence at the cross-sections of overlapping environments, which, from some broader perspective, are always and ultimately one and the same environment. Again, two sides of one coin. So though this may appear entirely obvious when considered in bite-sized chunks, the greater picture is not a simple one to hold on to. And so we shall have to unfold it in more detail across later chapters. But for now, in terms of emergent time, let us keep it in mind so we can attribute a context to claims like time emerges from the quanta of space. Because emergence is never a one-way street. Of course, there is always the obvious alternative to quantized spacetime, which is an infinitely divisible spacetime. But for our discussion, I don't feel that this really changes things, as it would only remove another flip side. It may remove our ability to measure a distinction between certain spatio-temporal relations at the Planck scale, but it doesn't deny the potential for an endless variety of states. Rules of nature would inevitably have to change as we continue down this ravine of infinite divisibility. If time is to be considered as malleable as suggested by relativity, stopping at the speed of light or flipping beneath the horizons of black holes, then there's no telling what an infinite division could bring. So, whether quantized at the Planck scale or warping into endless miniaturization, I feel that this is only ever a discussion about whether we will have the ability to identify these variants, these dualities of time. But the problem we are trying to untangle is what impact do these theories of time have on our understanding of self, the experiencer, bound to the physical, changing through time. As discussed, time is not universal. Your time is different to my time. Time is a web that warps and stretches depending on the location and speed of the observer. Our current description of reality above the Planck length is one of constant movement, all aspects of the universe existing at varying degrees of unrest, unceasingly moving through time towards entropy. Two perspectives from within this universe can be measured as moving in either space or time relative to one another, but not relative to some ultimate background of either an infinite space-time or even an infinite that surpasses space-time. But there was a key word in that sentence: measured. When we measure, we cannot avoid containing our descriptions to the finite. This is that quality of perspective so characteristic of emergence. The experience itself is a measurement. Being contained to a spatio-temporal mind, everything we can know in measurement will be finite. And a finite measurement, a finite experience can never entirely comprehend its own infinity. The above described quanta of time, of space, of energy, and of mass could, if proven, be used to satisfactorily describe a quanta of self, a description of the physical self in its measurable totality, the entire finite collection of Planck-sized bits that our existence has, does, and ever will fill. But even if we do choose to look at the information in this way, we can still appreciate it from two conflicting perspectives, two sides of the single coin. Above the limits of the Planck length, where each quantum of space-time is finite, measurable and seemingly independent from the whole, and below the Planck length, where this independence has no meaning or actuality, where we can only imagine a fog of interplay outside of space and time, where there is no here or there, no now or then, a unified, interconnected oneness. But regardless of which frame your perspective wishes to highlight, our independent experience, that which exists within space-time, and that which is at the core of our description of self, is as unique and whole as it is one with this infinite unity that encompasses it. Like our description of the infinitely large and the infinitely small in the very first chapter, these are not two separate realities. They are just two varied perspectives of the same unified whole. Again, we don't have the below Planck scrambling on the left and space-time on the right. These are the exact same space, only viewed through different eyes. So, the self that we first identified in the brain has yet to be refuted. The self is still the experience with all its finite restrictions of perspective, as it is also the physical, with all its limitations of physical reality. But equally behind our perception are these interpretations of self at one with all reality in their superposition of the infinite. The experience, it seems, is a finite attempt to describe this infinity of self. As Protagoras wrote, man is the measure of all things. Before I asked, are we the algorithm of the brain? Or are we the idea that arises from the algorithm? We are both, as both are finite descriptions, correct, yet infinitely incomplete.